Hello and welcome. I am Karen McFarland, the Punk Rock Professor, and I am here to give you clear and concise tools to help you crush chemistry. And what we're going to be talking about today is dynamic equilibrium. So first I want to talk about the concept of what we mean by dynamic equilibrium. And I have this analogy that I love to tell my students, and it has to do with a dance club that I used to see in the 90s in San Francisco called the End Up. So sometimes I was actually up early on a Sunday morning, I'm not sure why, but I would go past this place and people were just then starting to leave. It was like 6, 7 in the morning. So this is one of those places that maybe if you showed up at 10 p.m. you were way early. So what would happen here, as it happens with many dance clubs, is, and the End Up looked kind of like this, it was kind of this tall structure, is that people start showing up and the place is still pretty empty. So you have people that go in and then they start to fill it up. Okay, but it's still 10 p.m. and we're getting closer to midnight, and so more and more people are coming. Okay, so they're still filing in, and then eventually you're going to reach that limit where the fire marshal says no more. Okay, so that's when we have the bouncer at the door. Okay, so the bouncer at the door then stops people from going in, and we've got maximum. Okay, but what's going to happen? Of course, people are like, hey, let's hit up that other place. So people start to leave. And so then as those people start leaving, then the bouncers here start letting people in. Okay, so then we have this influx and this outflux. Now, what's going on here in terms of the total number? We have our total number is the same. Okay, so the total number of people stays constant. And I love the analogy because you can imagine everyone's in there dancing just like molecules. Okay, so there's a lot of movement, but it's always the same number. But they are different people dancing around as people are coming and going. And so that's this idea with dynamic equilibrium. So sometimes people think equilibrium means when the concentration stops changing. The concentration of the reactants in the product stays the same, so then you imagine the reaction's done, nothing's happening. The molecules are just sitting there. No, the molecules are still moving. They're going back and forth. The reactants are reacting, making products, products reacting, going backwards and making reactants. There is a lot happening. It is a dynamic equilibrium. And so that is the point, the concept I want to get across with this with my little End Up analogy here. Okay, so now let's look at some molecules. And as my sample molecule, I am going to look at hydrogen fluoride. Okay, this is a very creepy molecule. And when it's just hydrogen fluoride by itself, it is in the gas phase. So if we were to just look at HF all alone, it's not dissolved in water, it is a gas. Okay, so now let's imagine that we are going to take some of this hydrogen fluoride gas and we are going to dissolve it into water, and we're going to see what happens there. And so what I wanted to do is look at a couple things, and one is, let's just say we've got a beaker here with some water. Okay, and so we are going to dissolve that hydrogen fluoride gas into that water, and we are going to then create an aqueous solution. So the HF now, as soon as it dissolves in there, it is surrounded by water molecules, and now it is aqueous. And the second it becomes aqueous, then it can begin to react with the water that it's in. And so what we've got, as soon as we have dissolved it, this is the reactant that I want to talk about. So I don't want to talk about the gas, I want to talk about as soon as we dissolve it in water, what's going to happen. Okay, so this HF molecule, now it is hydrogen fluoride dissolved, and so once it's in water, now we talk about it as being hydrofluoric acid. Again, very creepy, very toxic. If any of you have seen Breaking Bad, you know what I'm talking about. Not good. Okay, so our hydrogen fluoride, or in this case now, our hydrofluoric acid, can then break apart in water, in aqueous solution. And so we've got now H plus ions and fluoride anions. Okay? So this does break apart to some degree, but as we talked about with this dynamic equilibrium, we have these two ions coming back together and reforming the neutral HF molecule. Okay, so here is our dynamic equilibrium that's going on. And another thing we can do that might help with visualizing this, so here we could draw even in this solution here that we have this breaking apart into H plus aqueous and fluoride aqueous. But we could also plot it out. We could create a graph where we look at the different concentrations of these various species that are in the solution and kind of give us an idea of what's happening over time. All right, so kind of like when we were talking about the end up and over time what was going on, let's look at hydrogen fluoride. And so I'm going to erase this. And let's plot this out. Let's plot out concentration on our y-axis, and time is going to be on the x-axis here. Okay, so let's think about this. That very instant that you put that HF into the solution, then you have pretty much that's all you have. The very instant you put HF into the water, it is 100%. It hasn't had a chance to react yet. So it is some concentration. We'll look at HF. It is some concentration of HF in solution. Okay, over time, what happens is it begins to react and break apart. And so the concentration of HF starts to go down as we begin to form these two ions. Okay, so we see this starts to go down, go down, go down. Okay, is this going to go down forever? Is it going to get negative concentration? No, eventually it will stop reacting and it will just flatten out over time. Okay, so over time this will reach some baseline concentration where it no longer changes. Okay, now let's think about H plus and F minus, okay? Our hydrogen ion and our fluoride ion. And let's think about what the concentration of H plus is at time 0. So this is time 0. Is there any of this time 0? No, because we're looking at HF before it has had a chance to break apart. So at time 0, there is none of the HF. Okay, so I'm sorry, there's none of the H plus, and there's none of the F minus, of the fluoride ion. Okay, so both of these are down here, and because this is a 1-to-1 stoichiometry, that they're going to be equal to each other, and they're going to be 0. All right, what's going to happen over time? They are going to increase. Okay, so this will go up by some amount. Okay, wow, it almost looks like they're going to be pretty much equal here. Maybe not quite, okay? So we've got this increase in concentration, and then eventually it's going to flatten out for both of those as well. So this is the point I want you to pay attention to, is this time here. Concentration has stopped changing. That's when you have reached equilibrium. Okay, so from this point on, we are at equilibrium. Okay, so we still have, remember, lots of molecules moving, they're going back and forth, but the total concentration has stopped changing. And then you're at equilibrium. All right, well, I hope that was helpful. We'll be, I'm sure, talking more equilibrium concepts and calculations in other videos. And thank you for watching. If this was helpful, like, subscribe, and now you've made it to the end, so here's your bonus track. And I want to tell you about the Gories. The Gories are an awesome garage punk band from Detroit. They are amazing, and they have this great song called Nitroglycerin. You've got to check it out. So thanks again for listening. Good job, everyone. Catch you next time.